You are provided with 12,2 grams of sodium sulfate. How many sodium ions would be in the sample? So the first thing that you need to do is you need to say, well, I'm going to look at number of moles is equal to mass over molar mass. And that is going to be equal to 14,2, which they gave me. And when we work out the molar mass of sodium sulfate, and PS, sodium sulfate is Na2SO4, because sodium has a valency of 1 and sulfate has a valency of 2. And the molar mass turns out to be 142. And then that is equal to 0,1 moles. Then they ask me, let's work out how many sodium sulfates there are then. So number of particles is equal to number of moles times Avogadro's number, which is 0,1 times 6,02 times 10 to the 23, and I land up with 6,02 times 10 to the 22. But that's sodium sulfates. I would like to work out how many sodium ions there are. And for every 1 sodium sulfate, there are 2 sodium ions. So what I need to do now is I need to double that number. So if you want to look at it as a mole ratio, you're going to have Na2SO4 is to the Na plus ion as 1 is to 2, and therefore I'm going to take this number and I'm going to double it, and therefore I land up with 1,2 times 10 to the 23. Which of the following molecules has polar bonds but is a non-polar molecule? So ammonia is a polar molecule, water is a polar molecule, oxygen is a non-polar molecule, and tetrachloromethane is a non-polar molecule. Oxygen has got non-polar bonds, whilst tetrachloromethane has got a slightly polar bond over here between the carbon and the hydrogen, but overall, because of its symmetry, is a non-polar molecule. Which intermolecular force is not present in a beaker of saturated salt? Now, what has saturated salt solution? Sodium chloride. It's got Na plus ions attracted to Cl minus ions. It's got Na plus ions attracted to water, and it has got water attracted to water. So that is going to be ion dipole, ion-ion, which we call ionic, and hydrogen bond forces. So the only one that is not in there is London forces. The following equilibrium exists in a saturated solution of sodium chloride. So they show me the dissociation of sodium chloride. When a few drops of hydrochloric acid are added to the solution, what gets observed? If I put hydrochloric acid in, I'm putting H3O plus ions and Cl minus ions into the solution, which means I'm going to have the common ion effect, and I'm going to land up favoring the reverse reaction, and we are going to see sodium chloride NaCl solid precipitating out of that solution. A catalyst is best described as a substance which changes the rate of the chemical reaction without undergoing any permanent change during the reaction. It does take part in the reaction, it does form part of the activated complex, but that is not the best description of a catalyst. And it may speed up a chemical reaction and it may slow it down, but the important thing is that it is involved in the reaction without undergoing a permanent change. When a reaction is at equilibrium, what can we say? We can say that the concentrations of the various substances remain unchanged, provided that no external conditions change, okay? So that seems like a reasonable answer. Just reading through the others, the reactions between the various substances cease. They don't cease, they keep going backwards and forwards. The amount of each substance is identical. That is not true. They just remain constant, but they're not the same. And the concentrations of all species in the closed system are identical. That's pretty much the same as the previous one, and it's not true. When some aqueous solution of sodium carbonate is added to a dilute solution of sodium chloride, what is going to happen? So sodium chloride has a pH of 7. Sodium carbonate, however, is going to have come from NaOH, which is a strong base, and carbonic acid, which is H2CO3, which is weak. So that's strong. That's weak, and therefore I'm going to become more basic, which means that the pH is going to increase. When hydrogen chloride gas is dissolved in water, an equilibrium is set up which can be represented. There you go. Which of the following combinations represent the two bases? So here we have, this is a proton donor, so that's acid 1, becomes, once it donates it, becomes base 1. This is a proton acceptor, base 2 becomes acid 2. So the two bases are the water and the chloride ion, and that is going to be answer C. The compound over here with two O's, this is a classic question, it's either going to land up being an ester or a carboxylic acid, because that's the general formula for an ester and a carboxylic acid, where you have CnH2nO2. So therefore, ester or carboxylic acid is D. And when alkenes undergo complete combustion, the products formed during the exothermic reaction are complete combustion produces water and carbon dioxide, so your answer is going to be C. A solution of potassium carbonate is known to have a concentration. Write the chemical formula for potassium carbonate, K2CO3, because potassium has a valency of 1 and carbonate has a valency of 2. What mass of potassium carbonate is present in 50 centimeters cubed of this solution? So now we're going to go through the whole process of number of moles is equal to concentration times volume, 0,02 times 0,05, and that's 0,001 moles. I then say mass is equal to number of moles times molar mass, and that is going to be the number of moles I've just established, multiplied by 138, which is potassium carbonate, which is 39 plus 39 plus 12 plus 3 times 16. And I land up with an answer of 0,138 grams. What volume of this solution would be required to make up a new solution in a volumetric flask? So remember that it's a dilution, which means we're going to keep the number of moles between the two flasks the same. And I'm going to first say, what is the number of moles that I require? And I'm going to take the information of the final solution. So that's going to be concentration times volume, which is equal to 0,015 times 0,25. Remember, we want it in decimeters cubed, so it's 0,00375 moles. Then we are asked what volume of my original solution would have that many moles in it. So I'm going to go volume is equal to number of moles times divided by concentration. My original solution's concentration was 0,02. and I land up with 0,188 decimeters cubed. So what would I have to do? I would be taking 188 milliliters or centimeters cubed, putting it into the 250 centimeter cubed flask, and then diluting, in other words, filling up with water to the 250 mark. Study the substances below and select one that meets each statement. Firstly, let's just do a bit of looking here. This is covalent. This over here is just pure carbon, which could either be coal, diamond is what they normally land up asking about, or graphite, which can conduct electricity even though it's a non-metal. Potassium chloride is a metal and a non-metal, so that's ionic. And carbon tetrachloride, we've actually just established, is also covalent, but it is a non-polar molecule. Whilst water is definitely a polar molecule. All right, so now that we've kind of given ourselves a little reminder, consists of polar covalent molecules, that must be your water. In the solid and liquid phase, the molecules are held together by hydrogen bonding. You've only got three substances, I suppose alcohols as well, but three main substances, water, ammonia, and hydrogen fluoride, and only water's in my list. Is a solid allotrope. Remember what allotrope means? It's the same phase, same compound, but different forms. So carbon has allotropes of diamond, graphite, and coal, as well as Buckminster fullerene, but you really don't need to know that. And so it comprises of an atomic lattice of covalently bonded atoms. That would be your diamond, and therefore it is carbon. Dissociates into ions in water. That means you need to have an ionic substance, so KCl. And conducts electricity when it's melted, but can't conduct as a solid. That is a typical characteristic of any ionic substance. So KCl again. And the fact that we never used methane, absolutely fine. Below is a graph showing the boiling points of various hydrides. Hydrogen fluoride, ammonia, and water have much higher boiling points than the trend would predict. You'd expect them to be down like that as their lines go. This is due to hydrogen bonding intermolecular forces. The question asks me, briefly explain what properties of nitrogen and hydrogen and fluorine cause the anomaly in the boiling points. Also explain how those properties result in such strong intermolecular forces. So you can't just say that it's because hydrogen bonding is stronger than expected, because otherwise you aren't explaining to me what properties and how. So I need both of those. So the first one is that the NOF gases have high electronegativity. They are also very small. Therefore, they, because of the high electronegativity, highly polar molecules form. When they bond with hydrogen, so hydrogen nitride, which is ammonia, hydrogen oxide, which is water, hydrogen fluoride, which is hydrogen fluoride, and therefore, what if you're going to land? You're going to land up with a strong force of attraction. Then your next thing is, because they are small, they are similar in size to hydrogen, therefore pack closely, and therefore stronger forces of attraction. Now we have this Maxwell-Boltzmann distribution curve, and it illustrates the distribution of energy in a given sample at two temperatures. It's how many molecules have got how much energy. That's what we're interested in. Temperature 1, lots of molecules have got little energy. So that is probably a low temperature, whilst temperature 2, more molecules, doink, have got higher energy. So that is probably a higher temperature. Which of the two graphs, T1 or T2, represents an energy distribution for the higher temperature? And it would be T2, and the reason would be because more molecules have more energy. Then it asks, use the kinetic particle model of matter to explain the significance of the unshaded area, area A. So all of these particles over here, okay, it doesn't really matter whether you do it for number 2 or for number 1 or for temperature 2. It's going to mean exactly the same thing. These molecules all have less energy than, let's say, particles have, than activation energy. Therefore, if they collide, they will not react. So that's pretty much it. They don't have enough energy to react.